Let's look now at section 8.2, and let's talk about integration by parts. When we look at integration techniques, so far we've had a few that are reminiscent of those techniques that we have when we differentiate. Integration and differentiation are both linear operations, which means if I take the derivative with respect to x of the sum or difference of two functions, then that's the same as saying I want to take the derivative with respect to x of the first one, plus or minus, depending on the operation that we had previously, the derivative with respect to x of g of x. This property is also true of integration. If I want to take the integral of f of x either plus or minus g of x with respect to x, that's the same as taking the integral of f of x with respect to x, and then plus or minus, as is appropriate, the integral of g of x dx. Okay? So the linearity property allows us to say we can take the derivative of a sum or difference by taking the derivative of each piece and then adding or subtracting. And the same thing is true for integration. We can integrate a sum or a difference by integrating each piece and then adding or subtracting as appropriate. Unfortunately, linearity does not extend to products and quotients. I can't just say I'm going to take the derivative of f times g and end up getting the derivative of f times the derivative of g. We need the product rule, as we saw in Cal 1. Well, same thing will be true for integration. We won't be able to just integrate each component, but how do we do it? Unfortunately, it's not quite the same as it is for integration, as it is for differentiation. However, the technique that we use for differentiation, namely the product rule, can show us how we integrate a product. All right? So go ahead and recall what's called the product rule for differentiation. And that's to say, we're going to take the derivative of a product. So if I could take d dx of f of x times g of x, that's going to require us to take the derivative of the first part and then times the second part. So the derivative with respect to x of f, and then that's going to get multiplied times g, plus the derivative of g times f. Right? And that's the product rule. So now let's say we want to integrate. Since these are all functions of x, I'm going to integrate with respect to x. If this is equal to this, then the integral of this must equal to the integral of that. So the integral of d dx of f of x times g of x dx is going to equal to the integral of all of this stuff. With respect to x. Okay, well now some of this stuff simplifies out a bit. After all, this is the derivative of a function with respect to x times the differential with respect to x. Well, this is just a differential. So here we can rewrite this just as the integral of the differential of f of x times g of x. That's the definition of a differential. The derivative of a function, or in this case the product of functions, the derivative of a function times the differential with respect to the variable. Well, that's the differential of with respect to the functions. And the same thing will happen here. After all, given this linearity property, I can take the integral of each of these on its own. But now, if I'm taking each of these on their own, that's going to be d dx of f of x times g of x dx plus the integral of d dx of g of x times f of x dx. But just like in this part, here I have the derivative of f with respect to x times the differential of x. Well, that's just the differential of f. So here I can write this as the integral of, this is, along with this, just gives us df of x. G of x is just a function, so here I'm going to say g of x times df of x, like that, plus the integral, and the same thing will happen here. If I take the derivative of g with respect to x times the differential of x, by the definition of a differential, as we see in Cal 1, this is just dg. So that's going to, let me write that first, f of x dg of x. And here I haven't changed this one, so let me just write that down the way it was. That's the integral of df of x dot g of x, like that. Okay. Well, now notice, this is the integral of the differential of the product. But the integral of the differential of a function is just that function. Right? The integral of the differential is just the function. It's like saying the integral of dx is just x. Here, that's a little more complicated than just x, but same principle. So here, this is going to give us just f of x times g of x is equal to the integral of g of x times df of x plus the integral of f of x times dg of x. Now, this looks a little intimidating to many people, because here we're not used to seeing df of x or dg of x. We're used to seeing dx or du or things like that. So we're going to use a quick substitution here. We can just say, and again, this substitution doesn't lend anything to the result. It doesn't make the result any more or less correct. It just tends to make it more palatable to people. It makes it so that it looks a little nicer. So here, this substitution is entirely for aesthetics, just so that it looks a little nicer. We're going to say take f of x and call it u. And they take g of x and call it v. And again, we could leave this exactly the way it is, but for aesthetic purposes, instead of df of x, which might look a little strange to some people, we'll end up with du. And that tends to be a little bit more palatable. So here we get f of, well, I guess I should be substituting, right? So that's going to be u times v. Okay, so u times v is equal to the integral of v du. Okay, so v du plus the integral of, again, that's your u, and then v is g of x, so that's dv, like that. And finally, we're going to go ahead and take this one and subtract it over to the other side. After all, that's just a expression that's being added to that other expression. So let's go ahead and subtract that over to the other side. Oop. There we go. So now that's gone, and we're left with the following result. I'm going to go ahead and write this one on this side. It's by itself, so I'm going to write it first. The integral of u dv is equal to uv minus the integral of v du. If we had left f of x and g of x, this would read the integral of f of x dg of x equals to f of x times g of x minus the integral of g of x df of x, which says the exact same thing, but looks slightly messier to many people. So this tends to be the preferred way of writing this. Note what this says. It says, I have the product of two things. I'm going to take the integral of that product of two things. That's going to equal to these two expressions multiplied together minus this other integral. This is called integration by parts. Essentially, you're separating this into two parts, the u and the dv. Integration by parts. And it is the counterpart to the product rule. If you're going to differentiate a product, you use the product rule. If you're going to integrate a product, you use integration by parts. Note that this technique does not give you an answer on its own. What it does is it changes this integral to a different integral. The idea being this integral might be one that I don't know how to do because it's complicated. But what I'm going to do is I'm going to trade this in for a different integral in the hopes that that different integral is going to be something simpler. I say in the hopes, it's not quite such a blind technique. We actually do go out of our way to make sure that things do work out in a nicer way by employing a few strategies, which we'll see here in just a second. Integration by parts is the first in a line of reduction formulas, which will take integrals, and instead of giving you the answer, which would be nice, but that's not what we have here. Instead of giving you an answer, it reduces it to a simpler form. This will be the first in the line of several reduction formulas that we see in this chapter. This is, incidentally, the most common one. This is the one you'll see more often than any of the other ones, although the other ones are quite useful in their own right. This one is central to just about everything because it's such a elementary operation. I'm going to integrate a product. Lots of things are the products of other things. So let's take a look at some examples of how to use this. And we're going to start off very simply with the integral of x times the sine of x. I'm going to keep things very, very simple, just like this. Okay, now here, x times the sine of x. We'll worry about our dx here separately. We're multiplying these two expressions here. Okay, so now, which one do I want to call u and which one do I want to call dv? Because that's what the integration by parts technique tells me. It tells me to think of my integral of a product. One of my expressions I should think of as being u. The other expression I should think of as the derivative of something else. Or I guess the differential of something else, dv. Okay, so which is which? This will not work 100% of the time, but the majority of the time. If something can be reduced to a simpler form by taking its derivative, that's what you're calling u. Everything else is what you're calling dv. So here, I notice the product of two things, x and sine of x. If I take the derivative of sine of x, I get cosine of x, which is different but not any simpler. It's still an elementary trigonometric function. However, if I take the derivative of x, I get the constant 1. And constants are simpler to work with than any variable, even a simple x. So here I could choose either one to be my u. However, if I choose sine of x to be u, the derivative of sine of x, cosine of x, doesn't make anything simpler. And the whole point of integration by parts is to change my expression to something simpler. Changing sine of x to cosine of x, it's a different trig function, but it's not any simpler. So here, what we're going to do is we're going to take u and call it that variable x. In general, anything that gets simpler when you take its derivative, choose that as u. If something is polynomial and something else in your expression is not polynomial, 99% of the time that polynomial thing will be your u. And it may not even be x, it could be x squared, x to the third, whatever. If it's polynomial in nature, most of the time that's going to be your u. Okay, so if that's my u, then everything else in the integrand should be my dv. And that includes the differential here, because after all, that's a differential. So this is sine of x dx. Don't forget that differential. You say, well, why? That's the part that matters, right? Sine of x? If I leave that off, who cares? In a moment, we're going to see where that is going to make a difference. So don't forget the differential. Okay, so we have our u. That's that one. We have our dv, which is that one. So now to use integration by parts, take u and find a differential of u. Okay, so that's going to be 1 dx. Take dv and find an integral. Okay, so that's just going to be v. And the integral of this, the integral of sine of x dx, is negative cosine of x. Like that. Yes, there is a plus c, but we're going to save that until the very end. Right? We're going to worry about that at the very last step. Technically, there should be a plus c here, but that gets absorbed into the final constant at the end of the problem. So u, find du. U, find du. dv, find v. Once you have that, your result won't be your final answer, but it'll be a new integral. That new integral, assuming we did things correctly, should be simpler than the integral we started with. The integral that we want is going to be u times v. Okay, that one times that one. So negative x cosine of x, that's going to be your uv, minus the integral. And then once you have this, you're going to subtract away the integral of v du. So that's going to be minus the integral. There's your v. And then there's your du. You can write 1 dx, or you can just write dx. Okay? So that's uv minus the integral of v du. Okay? So now we can simplify this a bit. Notice minus and minus, we just write that as a plus. So it's going to be negative x cosine of x plus the integral of the cosine of x dx. Notice we're not done yet. We still have an integral to find. But notice that this integral is much simpler than the one before. We know how to do that one. The integral of the cosine of x with respect to x is the sine of x. And then at our very last step, once we've integrated everything all the way through, now we'll worry about putting our constant at the end. And there we go. So the integral of x sine of x with respect to x is going to be negative x cosine of x plus sine of x plus a constant. And that's our result. Note that sometimes you're going to have to use integration by parts multiple times. So for our next example, let's consider, in fact, let's use something very similar to this one. Let me just take this x and call it x. Let me use x squared instead. So let's take the integral of x squared sine of x dx. All right, now we're going to do the same thing. We're going to take whatever expression simplifies when you take its derivative. In this case, the derivative of sine of x is cosine of x, whereas the derivative of x squared was 2x. So you either have one trig function changed to another, or you have a quadratic polynomial changed to a linear polynomial. And that's definitely going to become simpler. In general, if you have something that's polynomial and something else that's not in your integrand, then the part that's polynomial is a good choice for your value of u. So here we're going to take u to be x squared, and we're going to take everything else to be dv. So that's sine of x dx, like that. Okay, so now, if that's u, the derivative times the differential is going to be our new differential. du is going to be 2x dx. And if dv is equal to sine of x dx, well, then that means the integral of sine of x dx, which is negative cosine of x, that's our v. We'll worry about the plus constant at the end. So here, the integral of dv gives us our v. Okay, so now we're going to write a new integral. Note this doesn't give you your result. It just changes this integral to a new integral. We're going to have u times v. Okay, so multiply those together. Cosine of x times a negative 1 times x squared. All right, well, that's negative x squared cosine of x. Looks like that. Minus the integral of, here's your v, times your du. So that's going to be minus cosine of x times 2x dx. We can clean that up. Double negative makes that a positive. Take the 2 and factor that out. So this will give us minus x squared cosine of x. Double negative makes that plus. Factor out the 2. Integral of x cosine of x dx. Be very careful not to factor out the x. You can only factor out constants. Every semester I have someone who tries to factor out the x, and that is wishful thinking. It would be nice if we could do that, but that's not valid. So here we get plus 2 integral of x cosine of x dx. All right, so now notice that you have changed one integral to another. But also notice that this integral, even though it is simpler than the one above, right, that's gone from a quadratic down to a linear, it's still not something you can do off the top of your head. Okay, so we can't just say, okay, here's the answer. But the other thing you should note is that this is the product of two expressions, x and cosine of x, which means we're going to use integration by parts on this part. So here, let me do that in a different color. I'm going to take the integral of x cosine of x dx, and just this part. Everything else is already the way it is. I don't need to integrate any of this stuff. Just this part here. So here I'm going to do that again. I'm going to take a u, and I'm going to take a dv, and find a du and find a v. The choice should be the same choice that we had before. We chose x squared as our u, so our du became 2x dx. That's where this x came from. So now that should be your choice for u again. Otherwise, you're just going backwards. Here, you took its derivative, but then if you choose this to be dv, you're going to take its antiderivative, and then you're just back where you started. So you don't gain anything from that. So here, take that x that came from your original choice of u, and now make it your u for your second round. Everything else is going to be your dv. So it's going to be cosine of x dx. And now we can go ahead and integrate this one. The integral of the cosine of x is the sine of x. So our v is sine of x. We'll worry about our plus c at the end. The derivative of x is just 1. So the differential, du, is going to be 1 dx. Or we could just write dx, since the 1 doesn't really do much. All right, so now just this part right here. That's going to be, and again, I'm ignoring this stuff over here, just in the box. I'm going to take u times v. Okay, so that's x times the sine of x, u times v, minus the integral of v times du. Well, v is the sine of x, and du is dx. So sine of x dx, like that. So note now that this is an integral that we can take. So now we can rewrite this, substituting this in here. So we get negative x squared cosine of x plus 2 times all of this. Here I'm going to distribute my 2 so that it's 2 times this one and 2 times this one. After all, the 2 multiplies the entire expression. So that's going to be 2x sine of x minus 2 integral of the sine of x dx. And now, this integral is one we can take. The integral of the sine of x with respect to x is negative the cosine of x. So here we have negative x squared cosine of x plus 2x sine of x minus 2 times negative the cosine of x plus a constant of integration. Here, these two multiply together, and we end up with negative x squared cosine of x plus 2x sine of x. That makes plus 2 cosine of x plus our constant of integration. Note that it took 2 iterations, 2 uses of integration by parts, once to simplify it down, but then a second time to simplify this portion down to something we can handle. Once you trade it down to an integral that you can handle, that integral can be taken, and the entire expression is our antiderivative, just like that. So go ahead and give this a try. Take the integral of 3x times e to the 2x dx. All right. Go ahead and give that a try. Pause the video and give yourself as much time as you need. And then once you have a result, go ahead and unpause the video and we'll do it together. All right, so here we have a product. This is polynomial in nature, so that's usually going to be a good choice for u. It's not always true, but often it is. So if that's your u, then everything else is your dv. Just like that. Okay, so now, if that's u, then du is simply 3 dx, and v is going to be the integral of this expression, which is going to be 1/2 e to the 2x. We could say plus c, but we're going to leave that till the very end. So there's our antiderivative. And so now, this integral can be rewritten as u times v, 3 times x, times 1/2 e to the 2x, minus the integral of v times du. So that's going to be 1/2 e to the 2x times 3 dx. We can rewrite some of these expressions. Here, let's multiply this together. So this will give us 3/2 x times e to the 2x minus, take that 3 times 1/2 and factor that out. So that'll be 3/2 the integral of e to the 2x dx. But now that's an integral that we can do. The integral of e to the 2x, that's going to be 3/2 x e to the 2x minus 3/2 times, and when we integrate e to the 2x with respect to x, we get 1/2 e to the 2x plus a constant of integration. Once we've gotten rid of all of our integrals, we go ahead and place our constant of integration there. And note here, these can be multiplied together. So as our final result, we get 3/2 x e to the 2x minus 3/4 e to the 2x plus a constant of integration. And then here, there's different ways people write this. Some people will factor out the e to the 2x as a common factor. This will suffice right here. This is good. So this is our integral. Now, in some cases, the integration by parts uses one iteration. In other cases, it'll use 2 iterations or 3 iterations, as we saw just a moment ago. Note that if you have more than 2 iterations of integration by parts, the problem can become very, very long. Because of that, we have a way of organizing integration by parts that's used multiple times. If you're going to use integration by parts once, just do it this way. It doesn't save you any time to do it any other way. If you're going to do it just once, find your u, find your dv, find these derivatives and antiderivatives, and pop everything in. If you're going to use it twice, like we did in this example, you might want to use the other technique that I'm about to show you, or you might not. It's not really any longer, it's not really any shorter. It's just a matter of choice. But if you're going to use integration by parts 3 or more times, you definitely want to use this technique that I'm about to show you. This is still integration by parts, but it's just a different way of organizing your answer so that you don't have to write out 2 pages worth of information. So we're going to be using a table to organize the results of integration by parts. Note, if you're using it one time, this is actually longer. You're better off just doing it this way. If you're doing it twice, it's kind of up to you. It's the same one way or the other. If you're doing it 3 or more times, you almost certainly want to use this because it's going to be a lot shorter than writing it all out in full detail, or rather using this full detail. So let's take a look. Let's take the integral of x to the 4th power times, let's go back to the sine function, sine of x. Again, there's nothing special about sine of x, cosine of x, and e to the x. I'm just using them over and over again because these are functions that we know how to handle, right? This integration by parts, whether it be this way or with the table, you can use any product of functions. But here I've been using polynomials, sine, cosine, and exponentials just because those are nice and easy for us to handle. In a moment, we'll see some integration by parts where we use other types of functions. So here we're going to make the same kind of choice. We're going to take something and call it u, and we're going to take something else and call it dv. Okay, so here, this is polynomial in nature, so it's probably a good choice for u. Okay, so I'm going to take x to the fourth and I'm going to write it down right here. Now, on the line above that and a little to the right, I'm going to write down the other expression here, which is my dv. Now here, I'm not going to bother writing the dx. You say, well, wait a minute ago you said that the dx was going to matter, right? Whenever we use this integration by tables technique, this expression right here will be inconsequential. The times when it'll matter, this table is not a valid thing to do anyway. We'll see that in the next example. We're going to see one where this is something that we want to, it's going to be central to what we're looking at. And in that case, we won't be using this kind of table anyway. So if you're using this table, it's because you have something that's polynomial and something that's not. And in those cases, this dx, yes, it's part of the differential, as it is up here, but it's not going to cause us any harm if we ignore it temporarily. The times when this does cause harm to ignore, we wouldn't be using the table in the first place. All right, so here we go. We're going to take the thing that you want to call u, you're going to write it down here, and the thing you want to call dv, we're going to put that right here. And make sure they're on different levels. If you have lined paper, that's all the better, but if not, make sure you make some lines yourself. You want this one level below this one. And that's how we're going to organize. That's how we're going to keep things straight without having to fill up an entire page worth of information. Okay, so now what you want to do is you want to take derivatives of this until you reach 0. I say, what do you mean? I mean, keep taking successive derivatives. What's the derivative of x to the fourth? Well, it's 4x to the third. Okay, now what's the derivative of 4x to the third? Well, that's going to be 12x squared. What's the derivative of 12x squared? Well, that's 24x. What's the derivative of 24x? Well, that's 24. What's the derivative of 24? Well, that's 0. Okay, stop now. Keep taking derivatives until you reach 0. Now for this expression, you're going to take antiderivatives. Take the antiderivative of the sine of x. Well, that's negative the cosine of x. Okay, now take an antiderivative of negative the cosine of x. Oh, that's negative sine of x. Okay, take the antiderivative of negative sine of x. Oh, that's going to be cosine of x. Antiderivative of cosine of x is sine of x. Antiderivative of sine of x is negative cosine of x. And you can stop there. So, between each of these, you're going to place either the number positive 1 or negative 1. And you're going to do it in an alternating fashion, starting with positive 1. The reason we need this positive 1, negative 1, positive 1, negative 1, remember integration by parts is uv minus integral of v du. But if you use it a second time, you'll have minus a minus, which will change it to plus. And you use it a third time, you'll have minus a minus a minus, which will change it back to minus. So every time you use integration by parts, this negative will change to a positive and then back to a negative and then to a positive and then to a negative and so forth. So here it's going to have an alternating sign. So we take care of that by placing this negative 1 to compensate for that changing sign. So positive 1, negative 1, positive 1, negative 1. You always start with a positive 1 at this level where the u is. Like that. And now what you're going to do is you're going to multiply these three expressions together, plus that multiplied together, plus that multiplied together, plus that multiplied together, plus that multiplied together. And that'll be your result. So here, this gives us, okay, multiply these together, that's going to be negative x to the fourth cosine of x. Plus, okay, now multiply these together. Okay, that's double negative, that's positive 4x to the third sine of x. Now multiply these together. Okay, so that's 12x squared times 1 is still 12x squared times cosine of x. So plus 12x squared cosine of x. Okay. Now multiply these together. Notice we're just going down the line. Multiply these together. That's going to be negative 24x sine of x. So we're going to add that in. We're adding a negative, so I think I'll write a minus instead. So instead of plus and negative, I'll just say minus. Minus 24x sine of x. Here, multiply these together. That's going to be minus 24 cosine of x. So I'm going to be adding a negative, so let me just write that as a minus. Minus 24 cosine of x. And we're done. Here, anything times 0 is 0. So you have no more terms left. But don't forget your constant of integration. And that's our result. If you're using integration by parts once, you're better off doing this. If you're doing it twice, it's kind of up to you. Some people like this way a little bit better. Other people like to see it this way a little bit better. It's really it's up to you. If you're doing integration by parts 3 or more times, you definitely want this. Otherwise, it's a very long process. And that's our result. So here, start with your u, differentiate till you get to 0. That's how you know to stop. Start with your dv one level above that. Integrate. And now starting from this level, where your u is, positive 1, negative 1, positive 1, negative 1, all the way down. Multiply, that's your first term. Multiply, that's your second term. Multiply, that's your third term. Multiply for your fourth term. Multiply for your fifth term. Once you reach 0, add your constant. And that's your result. So go ahead and give this a try. You're going to use the integration by table. It's going to look just like this. Go ahead and give that a try. You definitely don't want to do this the long way. This one's going to be a long one if you do. Go ahead and integrate x to the 5th. Oh, let's make this e to the 1/2 x dx. Okay, so go ahead and pause the video, take the time that you need, and then when you have your result, go ahead and unpause and we'll go through it together. All right, so same idea. I'm going to take this and call it u. It gets simpler when I take its derivative. This one, no matter how many times I take its derivative, it's never going to reach 0. It's always going to be e to the something. So let's take u and dv, and we're going to put dv one level above u. Notice you never actually use dv anywhere in your result. You only use these down here. All right, so we're going to take x to the 5th power, and we're going to call that u. And now you're going to take derivatives until you get to 0. So that's 5x to the 4th. That's 20x to the 3rd. That's 60x squared. That's 120x. The derivative of that is 120. And the derivative of a constant is 0. So that's how you know you're going to stop once you reach 0. dv is this expression here, e to the 1/2 x. Really, it should be e to the 1/2 x dx, but we'll just worry about this part here. And if we integrate this, that's going to be 2e to the 1/2 x. And now just keep integrating until you reach this level, until you get to 0. So that'll be 4e to the 1/2 x. That'll be 8e to the 1/2 x. That'll be 16e to the 1/2 x. 32e to the 1/2 x. 64e to the 1/2 x. And then that's how you know to stop once you reach 0. Here you could go one further, but anything times 0 will be 0 anyway, so it's kind of a waste to do one more. And now here that's plus 1 minus 1, plus 1 minus 1, plus 1 minus 1. Okay? Notice your results don't always have the exact same pattern as this. It's when you multiply these together, that gives you each term. So sometimes it'll be plus minus in the terms, but in this case it was minus plus minus minus plus. So this isn't always a pattern that will appear at the end, but this pattern does need to appear here in the interim. Okay, so now we can write down our result. Take these and multiply them together. That's going to give us 2x to the 5th e to the 1/2 x. Like that. And then we're going to take this and multiply it together. Okay, so that'll give us 20 x to the fourth. Oh, but that's a minus. So minus 20 x to the fourth e to the 1/2 x. And then here, same thing. That's going to be plus 160 x to the third e to the 1/2 x. X to the third e to the 1/2 x. And then this one multiplies together. Oh, let's see, what is that? 60, 90, 930. So that's going to be minus 930 x to the second e to the 1/2 x, like that. No, that's not right. 16 times 6 is 60. Oh, 96, 960. There we go. The next one would be this one. So we're going to add 120 times 32. That'll be 3840 x to the first power. We can just write x e to the 1/2 x. And then multiply these together, which is just double what we had before. Right? That's the same number. That's just double the number. So that's going to be minus 7680. There's no more x on this one. E to the 1/2 x plus our constant of integration. And as big and clunky as that might look, it's definitely a lot simpler than having written it out by doing, oh, what would that be? 1, 2, 3, 4, 5, 6 integration by parts. That would not be nice. Or actually, this would be 5 integration by parts and 1 final integration, just a regular integration. Here, the way this textbook tends to write problems, they'll take common factors and factor them out. Notice here, every one of our expressions is an even number times e to the 1/2 x. So this book tends to write things this way. They'll have 2 e to the 1/2 x times, and then they'll write everything else. So that'll be x to the 5th minus 10x to the 4th plus 80x to the 3rd minus, what is that? 480? Yeah, half of that will be 480x squared. Half of that one would be 1920 plus 1920x minus half of that one would be 3840x, like that. Oh, no x, 3840 plus your constant of integration. Either of these is acceptable. The textbook tends to write things this way. This means the exact same thing. So that would be our result. Or the one above it would be fine as well. So now we've seen the standard ways in which we can use integration by parts. And it really is just the counterpart to the product rule. If I want to take the integral of a product, then integration by parts is a good technique. However, there are some times where you're going to use integration by parts in a time that doesn't look like you should. Let's consider, for example, let's find the integral of the natural log of x dx. You might look at that and say, oh, I know how to do that. And then you think and go, well, yeah, no, actually I don't. I've never seen that before. I've seen the derivative of the natural log of x, and I've seen the natural log of x used a bunch of times in algebra and in Cal 1 and in this class. But we've never done something as seemingly simple as integrated. So how do we do that? Well, obviously integration by parts shouldn't work, right? The integration by parts requires you to have the product of two things. Here, it's just the natural log of x that I'm trying to integrate. There's nothing else here. Well, sure there is. That thing right there. This differential can be thought of as 1 dx. And so we can treat this as one of the factors in our integrand. Essentially, what we want to do is we want to think of this as being the integral of the natural log of x times 1 dx. Those two clearly mean the same thing. 1 times anything is itself, but now written this way, it makes it a little more apparent that, yeah, maybe integration by parts will work, or at least it's something to try. Here, we may not know how to integrate the natural log of x. If we did, we would just say, oh, well, we know our answer. Okay, well, if we don't know how to integrate this thing, the only thing we know how to do is differentiate it. That must mean that is our value of u. So we can say u is equal to the natural log of x. It can't be dv, because if it was dv, we would have to integrate it to get v. And we don't know how to integrate it. That's the point of this problem. So here, u is the natural log of x, which means dv must be that 1 dx. Or you can just say dx if you like. All right, well then the integral of 1 dx is going to be just x, the integral with respect to x. Here, the derivative of u is going to be the derivative of the natural log of x, so the differential of u must be the derivative of the natural log of x dx. Well, we know the derivative of the natural log of x, it's 1 over x dx. So, because of this choice of u and dv, not that we had much of a choice to begin with, we can now say this is equal to u times v, so x times the natural log of x, multiply these together, minus the integral of v times du. But notice, x times 1 over x, or in other words, x over x, that's just 1. So we can write that as x natural log of x minus the integral of 1 dx. And now we've gone from an integral we have no idea how to do to the simplest integral that you have in calculus. The integral of 1 dx is just x. So here we can write this as x natural log of x minus x plus a constant of integration. And that's our result. In general, if you're trying to take the integral of some single expression and you don't know how to find the integral of that single expression, but you know how to find the derivative of that single expression, you can take that integrand, call it u, take the differential, call it dv, and then use integration by parts. So you can take advantage of the fact that you may not know the antiderivative, but you do know the derivative. So go ahead and give this a try. Let's see. Let's have you try the integral of 4 times the arc cosine of x dx. Don't let that 4 distract you. You can just factor that out. Really, you're focused on this part right here, the arc cosine of x. So go ahead and pause the video and give yourself some time to go through that problem. And once you have your result, go ahead and unpause and we can go through it and check it together. All right, so let's go through that. Here, let me just begin by taking the 4 out. And that's 4 times the arc cosine of x dx. Okay, this is going to follow the same pattern we had before. I may not know how to find the antiderivative of the arc cosine of x, but I do know how to find the derivative of the arc cosine of x. So let me call that arc cosine of x, let me call that u. U is equal to the arc cosine of x. So dv is going to be that 1 dx. So if you like, you can just write dx. That's your u, dv. All right, well then v is just x. The integral of 1 dx is just x. Now the derivative of the arc cosine of x, you remember that's the same as the derivative of the arc sine of x times negative 1. So here the derivative of the arc sine of x is 1 over the square root of 1 minus x squared. But for the arc cosine, you multiply the whole thing by negative 1. So using this, that should be du, using this combination of u and v, we can now rewrite that integral that we want a different way. We can write this as 4 times, okay, this integral is u times v, okay, so x times the arc cosine of x, x times the arc cosine of x, minus the integral of v times du. So that's going to be minus x, oh, there should be dx there, x times negative 1 over square root of 1 minus x squared dx. Just like that. That 4 stays put. That's going to be u times v minus the integral of v times du. Like that. We can rewrite that just a bit. We can write that as 4x arc cosine of x. I'm just distributing that 4. Let me distribute the 4 out here. So that's going to be double negative makes that a plus 4 times the integral of, let me put that x in the numerator. So that's going to be x over square root of 1 minus x squared dx. And now that integral can be done with a nice substitution. Notice the derivative of 1 minus x squared is negative 2x, which is almost exactly what you have up here. So this integral can be done by just a nice substitution. It's not something that can automatically be done off the top of one's head, usually, although you might, you might have something like this memorized, but it is something that can be done without too much hassle because it's a u substitution. So let's do this over here to the side. The integral of x over square root of 1 minus x squared dx. I'm going to take this radicand and call it u. That's sort of an unfortunate choice that they use u and v here. Here I'm using u as a u substitution. So since I've already used u and v for stuff, let me use w here just to keep that from getting confused. I'm trying to do a u substitution, but since I've already used u for something, let me use a different letter. So w. I'm going to take 1 minus x squared and call it w. So that means dw is going to be negative 2x dx. Oh, well, I don't have a negative 2x dx. I just have x dx. Okay, so multiply both sides by a negative 2. So negative a half dw equals to x dx. Okay, so this can now be written as the integral of this x dx in the numerator. That's negative 1/2 dw. Let me write the negative 1/2 outside since it is a constant factor. We can just pull out x dx, that's negative a half dw. I'll pull the negative out, factor it out. And then that's going to be over, or I guess I should write that over here, dw, because now that's over the square root of 1 minus x squared, or in other words, over the square root of w. Here, you can even rewrite that a slightly nicer way. We can write this as w to the minus 1/2 dw, like that. So that now we can use the power rule. Okay? That's the same as that. So now using the power rule, we can say that's negative a half times w to the minus a half. We can add 1 to the power, which makes it w to the positive half, divided by the new power, which is the positive half, plus a constant of integration. Worry about that constant of integration at the very end. Here, these two numbers divide out, half divided by a half, and we're left with negative, these are gone, w to the 1/2, or if we prefer, negative square root of w. But of course, w is just a stand-in for 1 minus x squared. So right here, after our substitution, we can back substitute, and we get a result of negative square root of that w. Just like that. But that is the product. That's the product. That's the integral here. So now we want the product of 4 and that integral. So we can now write that as 4x arc cosine of x plus 4 times this integral here, negative square root of 1 minus x squared. And now we can put in our constant of integration. Finally, is there anything to simplify? Again, depending on who you ask, some people might factor out the 4 or not. Here, the only thing I'm going to do is I'm going to just say, well, plus a negative. May as well just write that as a minus. So 4x arc cosine of x minus for square root of 1 minus x squared plus some constant of integration. There was a bit of side work on this one, but it is still integration by parts. There's a bit of side work here to do that integral there. But aside from that, this is still this pattern here. And that's our result. Finally, note that the integration by parts technique is what's called the reduction formula. It takes a formula that, it is a formula that takes an integral and reduces it down to a simpler integral. It doesn't give you an answer directly, rather it reduces it to a simpler integral, which you may be able to do in a different way. That reduction formula can actually give rise to other reduction formulas. So here, we're going to go ahead and derive a formula that's used for other uses. Let's say we wanted to take the integral of x to the power of n times the cosine of x dx. And I say, well, what's n? Is it 1, 2, 3, 4, 5? Well, that's the thing. We don't know. Just some power of x times cosine of x dx. Here, you'd be surprised how little we actually need to have numbers in a lot of functions. Notice right here, there's no numbers anywhere in here. These are all variables. Yeah, that's a constant. We just don't know what it is. So I guess I shouldn't say we don't need numbers. It's that we don't need to know what those numbers are. We don't need constant values. Here, I can still integrate this. This integration will yield another, a more specific reduction formula. Kind of like integration by parts, but a little more specific to this kind of problem. So here, we're going to use integration by parts to yield a formula for this type of integration. Okay, well, I may not know what this is, but I do know for a fact that if I take derivatives of cosine forever, I will never reach 0. I know if I take the derivative of x to a power, it might take a long time, but eventually I'll get down to a power of 0. So here, this will never get simpler, no matter how many times I derive, but this one eventually will. So let me call that my u. U is equal to x to the power of n, which means dv must be everything else. In this case, cosine of x dx. All right, well, if u is equal to x to the n, then du is going to be the derivative of this times dx. Well, I don't know what that is. Yeah, but we don't need to know exactly what that is. We know the power rule works by taking that n, bringing it down, and then subtracting 1 from the power. So I may not know what n is, but I know the pattern. Nx to the n minus 1 dx. And here, dv is cosine of x dx, so v is the integral of cosine of x dx, which is just the sine of x. So now here, I can write this as u times v, so x to the n times the sine of x, minus the integral, so u times v, minus the integral of v times du. Okay, well, that's n x to the n minus 1 times sine of x dx. Notice n is some constant. We may not know what it is, but we know it's just a constant number, not a variable, because here we're integrating with respect to x as the variable. And because of linearity, we know we can take a constant multiple and factor it out of the integral. So that's going to be x to the power of n sine of x minus, this n comes out, integral of x to the n minus 1 sine of x dx. This is called a reduction formula. Same as, it's in the same category of formula as integration by parts, except that it's specific to this kind of integral. Notice the reduction formula reduces the power here. You're saying, okay, I can start off with something to the 5th power, and then this will be part of my answer. There's no more integral here. But then I have another integral here whose power is smaller than before. Hence the name reduction formula. You're reducing the complexity, you're reducing the power on your integral. This doesn't give you an answer. It simply trades in a power, it trades in an integral with a certain power for another integral with a smaller power. If this reduction is enough to give you an answer, awesome. If not, reduction formulas are often used iteratively. You use it once, and then you use it again to knock the power down a little bit more, and then again and again and again. This gives you a hint into where a lot of formulas come from. If you look in the back of any calculus book, you'll see a collection of formulas that say, hey, this integral is equal to this. And oftentimes they don't have numbers. They have A's and B's and M's and N's and thetas and X's. That's where a lot of these formulas come from. We take an expression and we generalize it. We don't know what the number is, nor do we care to know. We find the pattern, x to a power times cosine of x. And then we integrate and end up with not an answer, numerical or an expression, but we end up with a formula, which is where a lot of these things come from. We basically prove the results by generalizing more specific results, or in some cases, making more specific results out of more general ones, like we do here with integration by parts. And that is it for this section. This is the reduction formula. Notice that we don't actually have any numerical results here, nor did we actually ever find what the full integral was. We just have this is equal to this. So here we're going to derive, maybe derive is the bad word because that means derivative, right? Let's create a reduction formula. The word derive in math means something a little bit different from the word derive in everyday language, doesn't it? So create a reduction formula. So that is it for this section, and that is it for integration by parts. Make extra sure that you understand integration by parts very well, because it's going to be one of the more central techniques that we use. It's often used in combination with other techniques. With this one, along with linearity, you can handle a decent number of integrals now. Without this one, plenty of integrals will escape you. If you have any questions, comments, or problems, please make a note of those and reach out during office hours during our next meeting. And I hope everyone has a nice day.